Welcome, my friends! In this video, we will be discussing the difference between Type 1 and Type 2 errors with relation to hypothesis testing. If you didn't watch part 1 of my Introduction to Hypothesis Testing video about the null and alternative hypotheses, I highly recommend you check out that video first. In the last video, I mentioned that there are two hypotheses in any hypothesis test. The null hypothesis, which typically represents a status quo default position or historically accepted claim, and then we have the alternative hypothesis, a claim contradictory to the null hypothesis that needs to be researched. We discussed that the two possible decisions for a hypothesis test are to fail to reject the null hypothesis or to reject the null hypothesis. Sometimes we will make the correct decision, and sometimes we will make an error and adopt a conclusion that is false. The best way to understand the relationship between our conclusion and the truth of our hypotheses is through a table. Either the null hypothesis is true or the alternative hypothesis is true. Our conclusion will either be to fail to reject the null hypothesis or to reject the null hypothesis. To be extremely clear, failing to reject the null hypothesis means that we believe the null hypothesis to be true, and rejecting the null hypothesis means that we believe the alternative hypothesis is true. If the null hypothesis is true and we fail to reject it, we have made the correct decision. Failing to reject the null hypothesis when it's true is a good thing. Rejecting the null hypothesis when the alternative hypothesis is true is also the correct decision. If the alternative is true, we should be rejecting the null in favor of the alternative. If the null hypothesis is true, but we reject it, we have made what is called a type 1 error, sometimes called a false positive. We have concluded that the alternative hypothesis is correct, when in reality the null is actually the correct hypothesis. If the alternative hypothesis is true, but we fail to reject the null hypothesis, we have made a type 2 error, sometimes called a false negative. We failed to reject a false null hypothesis. If the null hypothesis is true, the probability of making a type 1 error is represented by the Greek letter alpha, which is often called the level of significance. If the alternative hypothesis is true, the probability of making a type 2 error is represented by the Greek letter beta. So we see that there are two types of errors, type 1 and type 2, which correspond to the probabilities alpha and beta. Ideally, we would like alpha and beta to be as small as possible. The problem is, we don't know if the null or alternative hypothesis is true, so we aren't sure which error we are subject to. If the null hypothesis is true, a type 1 error is possible, and alpha is the probability of making that error. If the alternative hypothesis is true, a type 2 error is possible, and beta is the probability of making that error. In hypothesis tests, the researcher sets the level of alpha, but the level of beta is typically unknown. So why can we know alpha but not beta? It's because alpha depends on the null hypothesis being true, and the null hypothesis always contains equality, such as mu equals 10. The equality portion of the null hypothesis tells us an assumed value of the parameter, which is needed in order to set alpha, the probability of a type 1 error. But beta is the probability of failing to reject the null hypothesis when the alternative hypothesis is true. The alternative hypothesis carries with it an infinite number of possible distributions, such as mu is not equal to 10. If we conclude mu is not equal to 10, what is the true value for mu? We don't really know. We only know that it's likely different from 10. We need a specific value for the parameter in order to calculate beta, which is generally not possible under the alternative hypothesis. We can guess or calculate multiple possible betas for different possible values of the parameter consistent with the alternative hypothesis, but we can never know beta for sure. The type 1 error rate, alpha, is often set to 0.05 or 0.01, meaning there is a 5% or 1% chance of making a type 1 error when the null hypothesis is true. Other values can be used, but 5 and 1% are the most common. Generally, if alpha is lower, that will increase beta, the probability of a type 2 error, so keep that in mind when choosing a level for alpha. The seriousness of a type 1 or a type 2 error depends on the situation, and there are many examples where type 2 errors are much worse than type 1 errors, or vice versa. Let's take a look at some examples. A machine is set to produce steel beams 4 feet long. We would like to test if the machine is functioning properly, or if the machine is out of alignment and needs to be adjusted. The null hypothesis is that mu equals 4 and that the machine is properly aligned. And the alternative hypothesis is that mu is not equal to 4 and that the machine is misaligned and needs to be adjusted. Let's think about what a type 1 and type 2 error would look like. Remember that a type 1 error occurs when we reject a true null hypothesis, and a type 2 error occurs when we fail to reject a false null hypothesis. Take a second to pause the video and think about what the type 1 and type 2 errors would be in this circumstance. Okay, a type 1 error occurs when we reject a true null hypothesis. This means concluding that the machine is misaligned when it is producing steel beams at the correct length. This might lead us to make unnecessary adjustments to the machine, which might delay the manufacturing process. A type 2 error occurs when we fail to reject a false null hypothesis. This would mean concluding that the machine is producing steel beams at the correct length, when in reality the machine is actually misaligned and needs to be adjusted. This could cause several beams to be created of the incorrect length, which might need to be scrapped, causing wasted time and materials. Arguably, the type 2 error is worse in this scenario. We really don't want to let a faulty machine continue to produce beams of the wrong size, so it might be wise to select a slightly higher level of alpha so that beta, the probability of a type 2 error, will be lower. Let's try one more. In the manufacturing and testing of a new vaccine, the efficacy might be unknown initially, but after clinical trials with tens of thousands of participants who receive the vaccine, a more definitive statement about the vaccine's effectiveness can be made. The null hypothesis before the clinical trials might be that the vaccines are not effective at preventing the disease, and the alternative hypothesis might be that the vaccines are effective at preventing the disease. What are the two types of error in this situation, and which one is more serious? Pause the video and think about your answers. A type 1 error means rejecting a true null hypothesis. This would mean concluding that the vaccines are effective at preventing the disease when they really aren't effective. A type 2 error would mean failing to reject a false null hypothesis. This would mean concluding that the vaccines are not effective when they really are effective. In cases like these, researchers would want to minimize type 1 error. We generally try not to conclude that any medication or vaccine works unless there is very good evidence for it. Type 2 error here still isn't good. If a vaccine works and we can't detect its efficacy, we are missing out on a possible major public health breakthrough. Luckily, with very high sample sizes, we are much more likely to make the correct decision, and clinical trials like these have tens of thousands of individuals trying a new medication or vaccine before any conclusive statements are made. Alright, my friends, that wraps up part 2 to our introduction to hypothesis testing. Join me in the next video where I will discuss the formal steps to a hypothesis test.